Welcome to the second part of the lecture 4.4 on instance-based learning. I will now talk about something called distance-weighted nearest neighbor algorithm, which is actually a pretty straightforward extension of the k-nearest neighbor classifier. If we consider that k-nearest neighbor classifier can be viewed as assigning the k-nearest neighbors a weight of 1 and all others a weight of 0, the natural extension is to also weight the nearest neighbors. That is, that the ith nearest neighbor is assigned a weight wi, from 1 to k, where k is the number of neighbors we consider. Normally one have to define a specific function that computes this weight. One rather common choice for that function is to take the inverse of the square of the distance between the instance to be classified and the training instance in question. But this function could also be some of those kernel functions that we will describe a little later in this lecture. So then there are two cases, of course, as for the k-nearest neighbor algorithm. So we have the classification version, where the output is a class membership. So actually then what happens is that the query instance is assigned the class label most common among its k-nearest neighbors, but where the vote of each neighbor is weighted with wi. So it's not an equal vote, it's a weighted vote. So in KN regression, where the result should be a property value, so we calculate this value as the weighted sum of a property values divided by the sum of the weights. So it's pretty straightforward extension from the normal k-nearest neighbor case. It's also possible when you weight that you consider to extend the k-nearest neighbor from k to all data items. I mean, this means that you would consider all data items in this process. So one can say there are two versions here of the nearest neighbor, that you keep to a normal k number, like in the original algorithm. We call that a local weighted method, or we can extend this to all data items, and then we call this method the global weighted method. So the normal weighted nearest neighbor algorithm can handle both classification and regression. However, in both cases, the algorithm approximates a target function for one specific query instance. That means for one point in space. So we have another concept here, locally weighted regression, which is actually where we extend this approach of regression from one point to a surrounding around a query instance Q. And if we look at the term, so there is a reason why it's called local, because we do regression not over the whole space, but we do regression based on data near to xq. And of course we still keep the word weighted here, that the contribution of the training instance are weighted based on the distance from xq. So the weights are defined typically by a function, and as you will see, we will call this kind of function a kernel function. But actually, generally, it's a function where the weight of an instance, the contribution of an instance is weighted, and the weight is higher close to the new instance, and is smaller further away. One can say that the kernel function moderates the original distance measure. That's the way we're looking at it. Regression, of course, is natural because we still aim at approximating a real valued function. And this function could be of any kind. It could be linear, it could be quadratic, etc. And you see in the picture below an illustration how that's going to look like. We have a certain point, and then we have some kind of weighted curve that determines the importance of the surrounding items. So a kernel function is a concept imported from non-parametric statistics. And one can say kernel is a window function that it's defined over a certain window. When the argument to the function is a distance measure, one can say that the kernel function is a moderation of the original distance measure, which means that the effect of the distance is moderated. A kernel is normally a non-negative real-valued integrable function, and for most applications, it's common to define the function also to satisfy some other constraints. For example, that the integral over the whole area beneath the function is 1, so the area is always 1, and also that the function is symmetric with respect to 0. And there are a lot of these functions, and they are exemplified in this graph. One can say that for all of them, apart from the uniform one, we can see a decreasing weight or importance for points or for distances further away from the center. I also want to mention another approach to instance-based learners that connect to what we talked about here, kernel functions. So kernel functions are also useful in a kind of weighted instance-based learners called kernel methods. The kernel function here serves as a similarity function. This kind of method typically compute a classification as a weighted sum of similarities. Actually, here in this with this approach, the class label are modeled as +1 numerically as +1 and -1, both for the class label of the tracing instances and for the output, the unlabeled instance xq. So in this approach, there is also assumed that there is the weight allocated to each training example, and that then we have this function k that measures the similarity between any pair of instances. And in this kind of approach, this kind of function is called a kernel function. So what we do is we sum a number of terms where each term is the weight of an instance, a certain instance, the classification is a certain instance which plus minus 1 is 1, and this kernel function between the target instance and the selected training instance. And then we take the sign of that sum, and that sign, the sign of that sum becomes then the class label of the target instance. So this is a pretty old method. It was the first instance of it was invented many years ago in the 1960s and was termed the kernel perceptron. Now we will switch to a few other but related topics. As you may have already understood, machine learning is a pretty complex field, and there are many concepts, many approaches, many kinds of algorithms, and there is no self-evident trivial categorization of all these things. So what I try to show you on these slides is how I want to talk about a few concepts in the rest of this lecture. So actually, the focus for the rest of the lecture with something called a support vector machine. And a support vector machine is a kind of scheme or type of algorithms which are an instance of something called binary linear classifier. And essentially the common theme for all of these is to look at the instance space and try to find lines or surfaces that distinguish between different classes. And for the word binary, of course, signifies we talk about two classes in the basic case. So this is a special kind of algorithm. However, I find it natural to discuss it here because typically the support vector machines work in an instance-based learning fashion, in the sense that this kind of algorithm does not build up an explicit hypothesis structure. So rather, it computes indirectly some kind of surfaces in the feature space which corresponds, one can say, to the hypothesis. So therefore, support vector machine, in my mind, is very much inspired by instance-based learning. The case is, though, that support vector machine, in its basic form, handles only the linear case. So if we want this technology to be able to handle non-linear case, we need to add something. And actually what we then do is that the trick is to map the instance space onto another space, so that in the new space we create, it's possible to handle it with linear methods. And the technology for doing that is termed kernel methods. So that's the logic of the rest of the lecture. A few words about binary linear classifiers. Such classifiers are both binary in the respect that they distinguish only between two categories or classes. They are linear in the respect that the classification is based on a linear function of the inputs. So each data item is characterized by a vector x of features 1 to n, we refer to the features of in instances X as AI of X. Associated with each instance is also a binary valued class label, C of X. So the goal of a binary linear class is to find a hyperplane, line or plane that separate, or something else in higher dimension that separates the instances of the two categories. The property of the instance space required for such a hyperplane to be found is called linear separability. Obviously, the linear classification can only handle linear separable cases. So you can see a very simple example of this to the right, the linear case, which is easy to find a line in 2 dimensions, and the case where a delimiting area clearly is not linear. So techniques that can handle the nonlinear we will call nonlinear classifier techniques. So this slide simply shows two other examples of hyperplanes. So, I mean, what's important to understand is that for an n-dimensional Euclidean space, a hyperplane is an n-1 dimensional subset. So this means that for if we have a 2-dimensional space, which we have to the left, hyperplane is a line. If we have a 3-dimensional space, the hyperplane is a plane, and so on. It's difficult, a little more tricky to illustrate how a hyperplane actually looks in higher dimensions. A support vector machine is a model for machine learning which operates in a supervised mode with pre-classified examples. It can also operate in an incremental model. It is an instance of a non-probabilistic binary linear classifier system, where binary means that it classifies instances into 2 classes, and linear means that the instance space have to be linearly separable. A vector machine can be used to handle nonlinear problems if the original instance space is transformed into a linearly separable one. It can also manage a flexible representation of the class boundary. It contains mechanisms to handle overfitting. It has also a single global minimum which can be found in polynomial time. So it has many nice properties. It's easy to use. It often has a good generalization performance. And the same algorithm can solve a variety of problems with very little tuning. A support vector machine, or SVM, performs binary linear classification by finding the optimal hyperplane that separates the 2 classes of instance. So it's a typical instance of a binary linear classifier. A hyperplane in an n-dimensional Euclidean space is a flat n-1 dimensional subset of that space that divides the space into 2 disconnected parts. In the 2-dimensional space, a hyperplane is a line dividing the plane in 2 parts, as an example. So new instances are mapped into the instance space and predicted to belong to one of the classes based on which side of the hyperplane they are positioned. One should observe here that the hyperplane is not directly stored or concretely stored as an hypothesis. It's rather computed on demand, which is typical for instance-based systems. The support vector machine can, in the default case, only be applied to linearly separable instance spaces. So in the basic form, it has limited coverage. So I want to give you an informal outline of the support vector machine algorithm. So it works like follows. So a small subset of instances in the borderline region between the main instance space regions for the 2 classes are chosen as cornerstones for the analysis. These instances are called support vectors. So as you understand, these have also given name to the algorithm. So the SVM algorithm aims at maximizing the margins around the separating hyperplane we look for, maximizing the distance between the target hyperplane and the chosen closest support vectors. So as you can see in the picture to the right, depending on we select the hyperplane or line in this simple case, the margins becomes more or less broad. So the algorithm aims at finding the maximum margin. And one can say that the optimal maximum margin hyperplane is fully specified by the chosen support vectors. However, there is an optimization problem that has to be solved, but this problem can be expressed as a quadratic programming problem that can be solved by standard methods. SVMs are very straightforward to apply in linear cases, but we also want to look into how we can apply SVMs in nonlinear cases and also in the cases of non-feature vector data. So as the SVM only handles linear separable instance spaces with instance expressed in fixed length real feature form, all problems that we want to approach with SVM have to be transformed into such kind of linear separable spaces. And typically, most cases, when we create a new space, in order to achieve the separability we want, that space will typically have more dimensions than the space we start from. So the simplest case, the most straightforward case, is that we still have instances expressed as feature vectors, and but the instances are so configured that they are non-linear separate. And this is where we will focus the rest of this discussion. The other problem, which is also important in all cases, is the problem of being able to apply a method designed for handling feature vectors for instance spaces where the instances are expressed in other forms. And I've already illustrated for you an example of that in the context of the cosine distance measure, similarity measure, where one have to, when we have instances that are texts, one have to map those texts, the features of those elements of those texts into feature vectors. And this goes for other things. It's, so you can see to the right examples of complex molecular structures. If those are the raw instances, those also have to be transformed into a feature vector form in order to use this standard kind of method. A key concept in our approach to transforming a nonlinear feature space to an equivalent linear space is to make the new space more high dimensional. A problem with that is that many times computations of instance coordinates in the high dimensional target space is often more complex and costly. Luckily enough, the SVM algorithm only needs a distance similarity measure between instances positioned in a linear separable space. So this means if you create a new, we map our original space onto a new space, which is linear separable. That's of course a requirement. If we do that, then we can see to that we define a similarity measure in that new space, such that the similarity measure is expressed in terms of the coordinates from the original space, which is more easy to compute. So to summarize, we define a similarity measure that is applicable and meaningful for the new high-dimensional space. The SVM algorithm can use those similarity measures. However, the detailed calculation of the similarity measures are defined via a function, which call then the kernel function, so that they are expressed in terms of coordinates from the original space. So then, of course, it's very much up to how we choose this function so that can work that way. And the clever choice actually is to define the kernel function in terms of the inner product of the mappings of the coordinates in the original space. So this scheme is what is called the kernel trick. Let's look at an example. So consider a two-dimensional input space and a three-dimensional target space with the following feature mapping onto the linear separable three-dimensional space. To the right, you can see what we're trying to do. We have a two-dimensional space where we have instances that are not linearly separable. What we now try to find is a mapping that maps this space into a three-dimensional space where the instances is more clearly linearly separated. So what we do is we choose a mapping. So actually we map an instance x1, x2 onto three new coordinates. With the first coordinate in the 3 dimensions is the square of the x-coordinate in the first, and the second coordinate is the square of the second, and the third is the square root of 2 times number 1 times number 2. So okay, so this is how we define it. So if we then look at 2 vectors, x and z, we can consider them, of course, both in both spaces, and we look at the similarity function in the 3-dimensional space, which we choose to be the inner product of x and z in that space, and then we expand that through a normal calculation using the definition of the mapping. And then it turns out that when we done that calculation, it turns out that that becomes equivalent, of course, depending on our initial choice of mapping, as the square of the inner product between the corresponding vectors in the 2-dimensional space. So this means that we fulfilled what I've said in an earlier slide, that we want to define a similarity measure in the higher dimensional space, but still being able to compute these distances in terms of the coordinates in the original space. So this is a very simple example how this can be achieved. So apart from extending the use of support vector machines from the linear case to the nonlinear case, which we now discussed extensively, it's also interesting to see how it can be extended to other classification scenarios. So one natural case is to see whether we can extend the use of this technology from binary classification to multiple class problems. The strategy here is then to reduce the single multi-class problem into multiple binary classifications problems. Because for each of the second, we can then apply the SVM technique. It's also possible, but maybe not as exactly as straightforward, but possible to modify the algorithm so it can handle regression, keeping most of the key properties of the algorithm. So this was the end of lecture 4.4 on instance-based learning. So thanks for your attention. The next lecture, 4.5, will be on the topic cluster analysis. Thank you.